Yeah. All right, so let's see, and do a couple things here. I guess I need to hit the share my screen so I can get my camera going here and my notepad. Nice. Oh yeah, this new feature. There it is. Okay. And let's see. All right, so number 20, or chapter 28, number 2 is your question here. Okay, so it says here, 2 1.5 volt batteries with their positive terminals in the same direction are inserted in series into the barrel of a flashlight. So maybe to get us started, okay, so here's one battery, and then here's another battery. So they're stacked together in series, same direction, okay? And of course, as we're adding voltages, this would be equivalent of 3 volts. That's why we would stack them there. Are inserted into series in the barrel of a flashlight. One battery has an internal resistance of 0.255 ohms and the other of 0.0153 ohms. When the switch is closed, the current is 600 milliamp occurs in the lamp. What is the lamp's resistance? B, what fraction of the chemical energy transformed appear as internal energy? So actually, let me kind of redraw this. So I'm going to put my first battery like this. It's got an EMF of 1.5, but it has an internal resistance of 0.255 ohms. Maybe we'll put a little box around that. So that's kind of one and the same. In fact, it have a little positive knob there. Okay. And then that's connected to another battery. So 2 would have a chemical reaction. And so an EMF of 1.5, and then trying to get out of the dry cell of a battery is a little hard. So we would have a resistance of 0. Make that a little bigger. 0.153 ohms. And so there's my second battery. So they're hooked in series. And then, of course, I guess there's a switch. So to turn the flashlight on and off, we've got a switch, okay? When the switch is closed, the current of, and so the current flows through, and so I'll call this the load or the filament of the battery. That's what we're trying to heat up and get it real hot so it'll give off light. Okay. And they're saying here that the current would flow through here, representing, now they say 600 milliamps. I'm going to write that as 0.6 amps. Okay. Occurs in the lamp. And then, of course, what is the lamp's resistance? All right, well, I'm just going to do a single loop. That's all we have. If you imagine this being closed, if you imagine me kind of starting my loop up here in the upper left corner here, I would go plus 1.5 minus, because the current would go around the loop. And so I'd be, if I'm walking around in a clockwise direction, I'm going with the current. So it's minus 0.255 times the current, and that's what the current is. And they tell me it's straight up 0.6, okay? Then another plus 1.5 here, and then going with the current, so it's another minus 0.153 for the resistance, and the current is 0.6. And then finally right here, which would be, again, with the current, so it's minus, and it would be the resistance times the current, and that would complete the loop. And so a single loop, so a single equation, Only unknown is R, and so a little bit of calculator work can give me that number. So I have 1.5 minus 0.255 times 0.6 here, plus another 1.5 minus the 0.153 times the 0.6. Let me just hit enter at that point. Oh, but that would be what we call the terminal voltage of it. In other words, the chemicals inside make a total of 3. They're 2 batteries in series, 3 volt. But as we're trying to get the current out, there is some loss of energy. That's what we mean by these internal resistors. And so it looks like we get a voltage that if we were measured it from one side of the battery terminal to the other, then it would be a little bit less. And so there it is, a little bit under 3. And so we've lost a little bit. So that's what this comes out to be. And then if you imagine moving this to the other side, all of that would be equal to this 2.755. So then if I divide that by the 0.6, I get the value of R. So if the bulb filament has a resistance of 4.59 ohms, then that would fit all those numbers with the internal resistance and the current of 600 milliamps. And so there is A. What is the lamp's resistance? And then so B, what fraction of the chemical energy transforms appears as internal energy? All right, well, I guess there's a couple ways we could do that. I'll kind of maybe split my paper a little bit. And it says fraction. So I guess I need to say, all right, well, how much is actually being delivered by the chemical reaction? So I'll put this as the chemical reaction, because we know that the power is current times the voltage. And so the stuff delivered by the chemical reaction is these 2 1.5s and 1.5s. So maybe I'll just call that 3 volts. So we got 3 volts worth of chemical reactions coming place. And the rate of that chemical reaction is 0.6 amps. That would be 0.6 coulombs every second. In fact, unit-wise, maybe I'll do the units up here, but an amp is a coulomb per second, and a volt is a joule per coulomb. That's how you end up getting a joule per second, which is a watt. So a combination of the energy per charge and the charge per second gives us energy per time, gives us power. So the chemical reaction is delivering, let's see, 6 times 3 is 18. That'd be 1.8 watts. So we're getting from the chemical reaction 1.8 watts. Now, the reason I split my paper is, where does that go? And I would say it goes into 2 pieces. One of the pieces is the heat, the internal energy of the internal resistors here. And the other one would be then the actual filament itself. And of course, those should add up to 1.8 watts. So when they say here, where to go, what fraction of the chemical energy transformed appears as internal energy, they're talking about this one, the heat. And so maybe I will do an I squared R plus an I squared R, where this is the energy of the resistors. I guess I could also do an I squared R for the light bulb itself or the load. And all 3 of these should add up if I'm doing everything all right. And so maybe that'll be a good check to see if I am doing it right. But the heat of this first one would be the 0.6 squared times 0.255. And the other one would be the current going through it, I squared, so that'd be 0.6 squared, and 0.153. And the energy going to the load or the light bulb would again be the 0.6 squared and 4.59. So just out of curiosity, I'll do those separate. 0.6 squared times 0.255. So it looks like 0.0918 watts are going to warm an internal energy of this battery. This one, 0.6 squared times 0.153 would be 0.0551 watts. And the bulk of the energy is going to the light bulb. So 1.652 watts goes to my light bulb. And like I said, just out of curiosity, let me add the first one plus the second one, plus the third one. And sure enough, it's 1.8 watts. So yeah, I feel comfortable with my numbers. But it's these two that I should focus my attention on, because these two added together are the heat ones. So, which is what I did here accidentally. So 0.147, I'll call it watts, is what's converted into heat. And let me read the wording carefully. What fraction of the chemical energy appears as internal? So the fraction then would be how much shows up, the 0.147 as heat compared to the whole thing. Okay, so 0.147 out of the whole thing, which is 1.8. And that is a fraction of 0.082. You wanted to write it as a percentage, but they actually deliberately said fraction. So maybe I should leave it as a decimal. And so it's 0.082, or I would like the percentage, 8.2% is going to warm the batteries, if you will. You might say is wasted energy that's not really being used onto your light bulb. Although even your light bulb has got a lot of wasted energy because it's making a lot of heat. It's making very little light compared to how much heat. So end result is we get light, but a lot of energy went to heat, both internal heat and the heat of the battery itself.
Yeah.
And let's see.
That was confusing for me.
Pardon me?
It was just that part B that was confusing for me.
Was it that the word, the fraction?
I mean, I think it was just saying the fraction of chemical energy. I wasn't quite exactly sure what they mean by chemical energy.
Yeah.
Referencing heat.
Yeah, there's a couple of words in there I can see can be challenging. And one of them is the chemical energy. And that kind of comes back to, okay, what, hopefully my picture made sense that when they said the chemical energy, they're talking about the energy coming from this voltage, from the EMF inside. That EMF comes from a chemical reaction. I'll just take the old school, I don't know if anybody, I bet there's still out there, the old copper and zinc batteries. They're all usually alkali batteries now, but just a simple take carbon and zinc and make a reaction, and that what is that, zinc carbide, I guess, is what it would make. And that was, that's the chemical reaction. And so, yeah, and something that we kind of shy away from. That's something that, we said, well, that's to be discussed in your chemistry class to understand the chemical reaction a little better. I think in those video lectures, I held up a battery, kind of an old school one where I cut it. You can see all the carbon and the zinc inside. All right. Well, I hope that was a good one.
Yeah, thank you.
Wasn't nearly as long as one with the whole matrix I talked about. I think it was getting close to 40 minutes.
If Sasha doesn't have a question, can we do a 24?
Sure. Yeah, Sasha knows a lot of times he's hanging around just trying to pick up some information, so that's good. But he also knows to throw it in the chat. So, but since you said it first, we'll try that. What number? You said 24, right?
Yeah.
All right. So let's try 24. I'll mark down the time for. And I'm marking the video here. It's 12:50. Okay. All right. So let's switch back over here to 24. All right. So here it says a dead battery is charged by connecting it to the live terminal of another car with jumper cables. Okay. So we're going to jump the cables. Determine the current in the starter motor and the dead motor. All right. Well, maybe you've been forced to do this. But if you have a battery that has gone a little bit discharged, maybe you left like a dome light open or something, and you've got 10 volts in your battery now because you left the dome light on all night. You got to go to class in the morning and like, oh no. And of course, you also have a pretty high internal resistance because you've used up so much of the good stuff, the sulfuric acid and the lead. Now you've got just a bunch of lead oxide and water around. So your internal resistance has gone high and your voltage has gone down. And with that being said, you're trying to start this starter motor. And the starter motor has a small amount of resistance, which you're trying to get enough current here that will turn the motor, because the motor's got to turn the whole engine. And that does create quite a bit of power. And something like this, they're saying just won't be enough. You hit the starter switch and maybe I should put a starter switch in here. And so you put a starter switch and you go to turn it, and there just won't be enough, to turn the motor over, and it'll just go, ooh, and the current will go racing through, but it won't actually turn the whole mechanism and turn the engine over, and the car won't start. So all you hear is just kind of this click sound, click, 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 click. And like, oh no. So really you need some more power. So that's where the jumper cables come in handy. And if somebody else has a car nearby, maybe they've got a good charged battery. And so here's a good battery, right? It's 12 volts, and the internal resistance is the big thing, 0.01. And so you can get a lot of current out through here and run your starter motor. Of course, once you hook it up, you'll also be driving current. Now, here's where it depends on how discharged your battery is. The current coming out of the good battery, we'll call it current number 1, when it gets to this node, will definitely go to the starter motor. So let me call that current number 2. But here's the part we're not real sure about. If the battery is somewhat good, it may actually contribute to currents going and starting the motor. But if the battery is significantly dead, it'll actually not help, but actually hinder starting the motor, because the current is then going to split off and go through the battery. You're essentially now recharging this dead battery while you're trying to start the car. And so you're siphoning off some of the current, not a good place to be, which is why sometimes with a really low battery here, you can hook up a even a new battery, and you're like, well, I know this was good. I just started my car. And you'll go, hey, I can't start your car. And that's because the current splits off and you're busily charging up their battery, which is why if you wait 5 minutes and then start the car, you've built this up that at least it doesn't redirect as much current. And maybe it has charged it up enough that then it can go the other direction. Now, not shown in this picture, I would make sure you always make sure that this car you're using to jumping is also started, because that'd be like another power supply hooked to it, because the car as it's running has a generator and that produces current. And so now you've got the current from the car generator, you've got the current from the battery. You can even rev the engine in the car a little bit, and that would add to this whole ordeal. But that's kind of me digressing into, you should really make sure the second car is up and running, and maybe even giving it a little throttle, so it's sitting there idling, or instead of sitting there and idling, you maybe bring up the RPMs to 1,500 or 2,000, and then try to start that car, because you've got the good battery in the car, you've got the good generator at a high RPMs, which can generate a lot of current, and then chances are you can still start that other car even when it diverts off. Or sometimes it's the other way around. Maybe the car that went bad is a big car with a big engine and a truck, and needs a lot of current, and you're trying to jump it with this little tiny two-door coupe, and you just need a lot of other current here. It's just good luck trying to start that car. Even your good battery just wouldn't be enough. You really got to get some more from your generator. Anyways, but like I said, I digress here. So let's just take the problem at hand, which is we have a new, it looks like what they call a live battery, a good battery, and a dead battery. So I'll add to my diagram dead, live battery as they have here. And here's the part that I wanted to extra and overly emphasize. I'm not really sure about current number 3. Current number 3 could be going down this way or the other direction. I'm just not sure. But here's the neat thing, and how the math plays out. We don't have to know. We can let the math decide for us. In other words, what we're really doing here is calling this direction the positive direction. And so if we solve for the current and it comes out to be positive, that means it's going in this direction. But if at the end we solve for the current and it's negative, that's saying it's negative of the direction we chose. That means it's the other direction. So the magnitude will still be the same. You'll just end up with a negative number. So never make a big deal out of what direction the current is. Pick one. Now, some of them, they're obvious. Like I know that the good battery being more voltage, being of less internal resistance, is going to come out of the battery and go this way. So I have no doubt that current number 1 is in this direction. If current number 1 came out to be a negative number, I would suspect more that I did the math wrong than I actually set up the problem wrong, because I'm sure the physics is pointing the current coming out of this battery. And then likewise, there is no battery here. The current's got to go down and through this resistance, if you will, the starter motor. And so current number 2, again, I'm 100% positive going to go in this direction. So I'm going to label it that way. That means when I do the math, it comes out positive. If I do something in the math and it comes out to be current number 2 negative, I'm just going to say, you know what, I don't believe it. I did something wrong in the math, because the physics is just very, very clear what direction number 2 is. So 1 and 2, I really know. And so I would encourage you, if you have things that it's just so obvious, that you pick the direction that you know that it's obvious. And so you know those are going to come out to be positive. I think that because we do that so often, students kind of shy away from negative numbers, but there's nothing wrong with negative numbers. I do prefer positive more. So I always pick a direction that if it's very obvious, I'll pick that as the positive. So that's why I pick number 1 and number 2 first and said, oh, that's clearly positive. That's clearly positive. It's the number 3 that it's impossible without studying the numbers and doing some math here to know what's going to happen. And again, I would just say this is pretty a low battery with a lot of internal resistance. I mean, look at that. This internal resistance is 100 times average. So it's really because of that. My gut's telling me that it's going to split off and be recharging the battery while you're trying to start the car, which is, again, going to be a hard thing to do, but maybe it's enough to do it. So I don't really know and don't really care. It doesn't really matter. I'm just going to run through the math and see if I get a positive or a negative, because I just don't know. But like I said, if I had to make a guess, I would say it is going down just because of that high internal resistance and that low voltage. So I think that's it. But know that if I come up with a negative, I'm not going to be bothered here. I would only be bothered if 1 and 2 were negative. All right, so let me do our loop rules. I might even ask myself, can I do equivalency? Right? We had this long discussion in the first Zoom one, is that equivalencies are really nice to do, but not everything can be equivalent. And this one, they're not equivalent anywhere. They're not series, they're not parallel. Maybe I should just kind of mention it. I'll take my maybe a red pen here and say, if you kind of look at this current coming from number 1, it hits this node and splits off, or is rejoined. I really don't know. But either way, the current does not go directly from this resistor to this resistor or to this resistor. So they are not in series. These resistors just aren't in series. And the same thing is they're not in parallel, because parallel, you would have to be able to connect their one side, I'll call it the top side, and I'll even color that in red here. So the top side of all the resistors are actually connected the same. So that's a good first step to think that they're in parallel. But the other side is not. See, if I take the other side of this resistor, I cannot get to the bottom side of the one resistor, or can I get to the bottom side of this 0.01 resistor without first crossing some other element, which changes the voltage, which means they're not in parallel. If there's a voltage change, they're not in parallel. Voltage or parallel means they have the same voltage. And with those batteries there, I can't put this one in parallel with either of these two. And for that matter, I can't put either of these two parallel with each other. And they're not in series. So series and parallels is out. So we got to go to something more advanced, but also more fundamental in its nature. And that's the conservation of energy and conservation of charge. That's what Kirchhoff noticed. That's why we call them Kirchhoff's laws. He said, well, just go back to the fundamental principles of conservation of energy and conservation of charge and work it out. So that's what we have to do. And so that's where we did a problem right before the break. That was at 40 minutes in the matrices. And I'll do the same thing. Now, fortunately, as you can see, I have 3 currents to worry about, because there's 3 branches, which means I'm going to need 3 independent equations. And you can always get your independent equations first by doing the loops, but then by doing the nodes. Now, be careful with the loops. I'll say the same thing I said last time, is that to make sure they're independent, why don't you do the small loops? Because if I do what I'll call the left loop and then I do the right loop, that's going to give me 2 equations and they are independent. But if I tried to do the big overall loop, I might accidentally think that that's a new equation, but it's not. It's mathematically just putting the first and the second equation together. And so that's not independent information. So I can't do a big loop. Big loops are always made out of smaller loops. So the easiest thing for me to always say is, if you do the smaller loops, that's the most loops you can do, and that's the most independent equations you can have. Now, I got to admit, sometimes it's nice to maybe do a big one and the left one. And as long as I don't do the right one, then I would have 2 equations. So I can do the big one. I don't want to say I can't do the big one. What I really need to say here is there are 2 independent equations, and the third equation is dependent on that. So if you want to do the left and right, good, just don't do the big one. If you want to do the big one in the left, fine, don't do the right one. If you want to do the right one and the big one, fine, don't do the left one. So any two of those would be independent, but the other one would be a result of that. And mathematically, you could see it. If I did the big one and the left one, and then I took the big one and subtracted off the left one, I would get the same equation as doing the right one. So again, I can only get two equations, which is why you have to do at least one, sometimes more, of the node rule, which is the conservation of charge. So know that you can't ever solve one of these equations by just doing the loops. You've got to do the nodes. You can't just do conservation of energy. You have to also do conservation of charge. And I'll do that one first, because I did it first last time. Doesn't matter which one we do first. But notice in my picture that current 1 comes in, it hits this node. And in my picture, current 3 goes down and current 2 wraps around. So what comes in, which is I1, equals what comes out, which is I2 and I3. So I would call that equation number 1. That's the node equation. The other two equations are the loops, a left loop and a right loop. So I'll go ahead and do the left loop. Maybe I'll start over here in the lower left-hand corner right here and just go clockwise. So as I go across the battery, I go from little to big. So that's plus 12. Then I have a movement in the direction of the current. Remember, I'm saying current number 1 is going this way. So I'm going with the current. That's where the minus comes in here. The resistance is 0.01 and the current is I1. Continuing around the loop till I get something besides a wire. Right here. Here's another resistor, and I'm going with the current. So that'd be a minus. And the resistance is 1 and the current is I3. Continuing on down, I would go across this battery and I'm going big to little. So that would be a decrease in potential. That'd be going from positives to negatives. And so that's a minus 10. And all the way back to where I started. So that's the sum of all the voltages around the loop. And I'll call that equation number 2. And I'll do kind of the same thinking with the right-hand loop. And I'll start in the lower left corner. From little to big is plus 10. Keep going. Here is a resistor. Notice I'm going against the current, so it would be a plus. And the resistance is 1 and the current is I3. Continuing on, I get over here to this part of the loop where I'm in current number 2 and I'm going with the current, so it'll be minus. And it would be 0.06 for the resistance and the current is I2. And that would complete the loop. And so the sum of all those voltage changes have to be 0. And that's my third equation. And these aren't too bad to do by hand, but they do take a little bit of time. And I'm going to just kind of use this opportunity to show you with the matrix again. Let me write this. Three equations as one matrix equation. Current 1, current 2, current 3. And so if I kind of look at this first equation, I would have a 1 times current 1. When I move this over, minus 1 times current 2. Move this over, minus current 3, and then left with 0. So this first row, this first column equaling 0 is mathematically this first line. It would be I1 minus I2 minus I3 all equals 0. So that first row is equivalent of equation number 1. Equation number 2, it looks like there is a negative 0.0 I1. There is no I2 and a negative 1 for I3. When I put these two together, that's a plus 2. Move it to that side, it's negative 2. So the second row, first column, would represent equation number 2 if you multiplied it out. You would go that times that times that equals that. And then finally, my third equation would have no current number 1 a minus 0.06 for current number 2, a plus 1 for current number 3, and then if I bring the 10 to the other side, that's a minus 10. So there is my matrix equation. And what I'm trying to show you, and for those of you who've gone or are in Math 210, you know that there's a lot of operations you can do to this matrix and manipulate it around. But if you get it into an identity matrix, so that then this equals A, B, and C, and these numbers would have to change, because in other words, to change this matrix into an identity matrix, we've got to go through a lot of math. And so whatever you do to your math equation on the left-hand side, you have to do the same mathematics on the right-hand side. And so that mathematics would change these. But here's the neat thing. When they get changed, when they're in this form, what this equation is saying is by having a 1 times I1, and then 0 times I2 and 0 times I3, it would just be equaling to A. So this first row and first column would be saying I1 is equal to A. And the same thing down here, this would be saying I2 is equal to B, and then this would be saying I3 is equal to C. And so that's what's neat about changing this matrix through a bunch of math into the identity matrix, because then on the other side, as you're doing the same math, this A, B, and C is the answers we're looking for, currents 1, 2, and 3. And I just put on here math because for us in our class, then we'll just actually then use our matrix. And so I showed this in the other problem, but just in case somebody's new to their calculator, I have the TI-84 and my matrix is under the shift key down here, which I think I mentioned last time. On the 83, it was on the, no, here's the 83 plus, it's under the shift 2. One of my calculators, it's not under the shift. I think maybe just the 83 without the plus. Not sure which one. But anyways, first thing you want to do is actually then input your information. So come over here to edit. And what we're going to input is this matrix. We're going to make 3 rows and 4 columns. The fourth column being what this all equals to. So we need to make a 3 by 4 matrix. So when you hit edit, first thing it'll do is say, how big do you want to make your matrix? Now, right before the break, we did this matrix and it was a 4 by 5. So now I'm just going to say, make it a 3 by 4 matrix. And so now I just have to enter. So I will go 1, enter, and notice it'll just move over. And so then -1, move over, -1, enter, and it'll move over, and then 0. And that will finish the first row, and then it'll come down to here. So that is a -0.01 enter. It'll go to here, which is 0 enter, -1 enter, -2 enter, and then it'll jump down to the third row, 0 enter, -0.01 enter, 1 enter, and -10 enter. And just to kind of double check, let me just kind of scan across. Looks like this last column looks good. I'll tab over -1, -1, +1. That looks good. I'll tab over -6, 0, -1, and then it's off the screen. So I got to scroll over and get 1, -0.01, and 0. So it looks like my matrix A is this stuff. That's good. I'll just quit that. So that's now stored as matrix A. But here's what I want to do. I want to do a bunch of math. And the process of this math is called reduced row echelon form, RREF. So that's the mathematical operation. It's sort of like if I wanted to do sine of a number. I go sine of 4, enter. Okay. And so it would give me the sine of 4. So what I want to do is RREF of matrix A. And you do that by going back to the matrix menu. and selecting now the math menu. Scroll down. And it's a little below on my screen. There it is, RREF. Just hit enter on that. And it'll put right on your screen, RREF. And so like sign, it wants, sign is, you need to take sign of a number. This needs to take the RREF, or the reduced row echelon form of a matrix. So you can't enter a number here. What would happen? I bet it would freak out. Yep, error. So let me try that again. So let me come back over here to math. Let me go to RREF. And let me go to matrix menu and select matrix A. Hit enter and hang on. All right, sorry about that. I had to unlock a locked door here real quick for the other members of my household here. It's like my son just got back from work there. All right. Okay, so where was I? So I'm doing the RREF. So this then is, well, what I said it would do is take that into the identity matrix, and then these would be the numbers you would get. So this is saying, put it up here, that current number 1 is 171.67. Current number 2 is 171.39. And current number 3, kind of my interesting question, is it positive or is it negative? And it did come out to be positive. So my guess was right, barely positive. And what's happening then is coming out of the new battery is quite a bit of current, 171.67 amps, although I say quite a bit, but actually this is kind of on the small side for starting a car. Yeah, they can be quite high, but small car. It would be good for a small car, I think. So here is, again, coming out of this car is this one. And then notice that most of the current certainly goes on through, which makes sense. I mean, this is fighting it not only to have higher resistance than the starter motor, but it's got a pushback voltage here. So you wouldn't expect much to go that way, but most of it then goes to the starter motor. A little bit is going in, I'll call it bleeding off and actually then charging the battery, but that's not the main purpose here. Charging the battery can occur later when this car gets started and the generator is then generating it. So hopefully this person will start it and drive for a while and charge up that battery. But most of it goes this way. So we did all three. I don't think the question actually asked for all three. It says determine the current in the starter motor. Okay, so starter motor would be current number 2. So there's current number 2. And in the dead battery. So this is the dead battery, including the direction. So we're actually charging up the battery. All right. Good. Hope that helps. All right, oops, not what I wanted to click on. Back to the Zoom on the big screen, see if anybody put anything into the chats. No. All right, so I think that was your question, Brendan. So
yeah, thank you.
Hope that helps. If you guys have another one for me. Or
22, if you don't mind.
22?
Yeah.
Okay. Let's try 22. Chapter 28. Number 22. Oh, let me write it over here also. Number 22 and the time 1:19. Perfect. All right, so I'm going to put page 1. I will anyways. Don't know if this will be a long one or not. It's 22. This is an interesting design. I think they purposely threw them at the diagonals because one of the challenges I should point out is, recognizing if something is in series or something is in parallel. And sometimes, especially parallel, we think, well, if they're drawn parallel, they're electronically parallel. And that is not the case at all. That was shown, I think, really well on this last problem we did. These 3 resistors are drawn all vertically. Oh, they're parallel because I've drawn them vertically. But it's not how you draw them. It's electronically how they're connected. And so we concluded that these were not parallel. And they were not series, which is why we couldn't do a simplified circuit or an equivalent circuit at all on this one. But I think the one coming up we can. And so I want to talk about that one a little bit better because I think there are some things that are parallel here that, and maybe even series. Well, let's just work through it. But again, if we can, maybe the thing to go is with the equivalents. And again, recognizing whether they're series and parallel can sometimes be a challenge. Let me just read the problem. It says, taking R to be 1 kiloohm and E, script E, I should say, 250 volts, determine the direction and the magnitude of the current in the horizontal wire between A and E. And I think E is, make it a little bigger. Is that lower right-hand corner? Yeah, A, B, C, D, E. Okay. All right. So let me kind of draw this. I'll start by drawing the battery on the left, which they say is E. And I'm just going to put 250 volts right away. And then they come up here, and they call this point B. So they call down here point A. And then there is a resistor of R, which they say is 1,000, or they call it 1 kiloohm. I'm going to put 1,000. And then it gets to this interesting puzzle piece here, which they call C. And this puzzle piece continues on straight, but it also angles down. The part that angles down and back comes over here to A. And they say that this is 4R. So let me just write it as 4,000. And the other one angling down is 3R. So let me write that as 3,000. And the one that continues across horizontally is 2R, which let me write as 2,000. All right, so I'll get to D. And then D comes down and goes another battery in here. And this has twice the EMF. So this would be 500 volts, or twice script E, before it comes down and meets at E. And then they come across and meet at A. All right, so let's talk here about the currents. Like I said, sometimes we know the direction of these currents, sometimes we don't. But maybe then just write a bunch of loops, although I'm tempted to do that because I know the loops always work. I got 1 loop, 2 loop, 3 loops. And I guess currents, I'd have 1 current through this way, 1 current through this way, 1 current through this way, and 4 currents with not worrying about this one. So 5 currents if I worry about this one, which I do eventually need to worry about that because it does say what is the current in the horizontal wire between A and E. So this is ultimately what they want. So it's going to come to a point where I need to know that. But part of me says, why don't we just make 3 loops and then 1 node, and then that would be 4 equations, and I can get the currents in each of these and kind of figure out what's going on from there. The other part of me says, maybe we should do an equivalence circuit here. So maybe I'll do an equivalence circuit, because this is a good one to illustrate that it may not look like it, but the 4,000 and the 3,000 are actually in parallel. And I'll call this the top of the 4,000 and the top of the 3,000. Notice they are connected without anything in between them. For that matter, they're also connected to the 1,000 and the 2,000. But the other side of the 2,000 cannot connect to the other side of the 3,000 without going across something else. And just like the other side of the 1,000 cannot go to the other side of the 4,000 without going through something else, I would have to conclude that the 2 and the 1,000 are not in parallel with the 4 and the 3, but the 4 and the 3 are parallel with each other. So I can put those two together and have an equivalent circuit that might look something like this. Where I still have this at 1,000, I still have this at 2,000. But this center one then is what is represented by the C connecting to, and I'm just going to put it together because, I know in the diagram they call this A and they call that E, but electronically they're all the same point because they're all connected by a wire, so they all have the same voltage. So I'm just going to call this one right here the equivalent of those. So to get 1 over equivalent, I need to take 1 over 4,000 plus 1 over 3,000 and solve it for this equivalent. All right, so let me take my 4,000, it's reciprocal, add it to the 3,000 and it's reciprocal. Hit enter and take the reciprocal of that. And it looks like we're looking at 1714. So 1714. Put 1714. All right. Now I question if that was a wise move, because now as I look at this, these are not in series. They're also not in parallel. So I'm going to have to do some loops at this point. And eventually then, if I do my loops at this point, I'll then have to take this equivalent and work backwards to see how it affects that one. And this was that same discussion I was having on number 21. I was asking myself was it better to do a partial equivalence and then work backwards, or was it better just to leave it as 3 loops? If you guys were around, you might remember that big long equation. It was number 21. It had like the 6 ohm resistor on top. And I ultimately decided to leave it as the original, and we figured out what direction the current is. So part of me thinks maybe I should backtrack to that, because it would, and I'll do that again. But since I didn't do it this way, part of me thinks I should do it that way. But I think this would be unnecessarily hard. I mean, why deal with the equivalent if I can do the real thing? Yeah. So all right. So this was a fun first step, but it probably is not the direction I want to go. It would be a little easier to have just 2 loops instead of 3 loops, but I'm going to go ahead and come back to this one. All right. So why don't I jump to page 2, but kind of put this picture here of page 1 real close so you can kind of see it here, because now I'm going to just say, let's write out these equations. So first, let's label it. Maybe I will label in green here. I have a feeling, and like I said, you don't have to be 100% accurate on this, but since this is the higher voltage, I'm sure this part of the loop dominates and the current comes pouring out of this 500 and arcs around. So I'm going to say this is current number 1. See, and then as this current comes through here, of course, it's going to lose some voltage when it gets here to C. But what that would mean, though, is it can tailor off back through this resistor or back through that resistor. So I'm pretty sure the current's going to go this way. I'll call that number 2 and go this way, which I'll call number 3. Of course, so far, I really haven't asked the question about this one. This one is a tough one to kind of judge because it's pushing the current this way, but this one's also pushing against it. And in a sense, it's 500, it's a lot more voltage. It wants to push through. And there's the question. It's 500, but it loses some of its potential through here. And then through here, it would lose more if it's going to overcome this battery. So is it enough to overcome that? Don't know. But see, if it didn't, that means this 250 would come up this way and lose a little bit here, as this came up and lost a little bit, and then the currents would go like that. And so it could be doing that. That might not be too much of a surprise. But given that they both lose something here, and this one is twice as much, I'm going to make a guess. And again, I want to emphasize, this is just a guess, that this one right here, this is the one I know the least about. I'm going to call it number 4. I'm going to guess, and purely guess, will not be bothered at all if I got a negative number. I would be bothered if these other 3 were negative. I'm sure that's happening. But this one here, I'm not real sure of. So let's just see what happens. It would be fun to see. Is this 500 enough to overpower and we're essentially then charging up this battery? Or do we lose so much here that all of number 1 dumps down into here, plus some comes out of this battery and dumps down into here? And so these 2 currents then would be made up of 2 flowing in. But that's not my guess. My guess is going to be number 4 arcing around this way. And so my guess is that this 500 is so strong that even though it loses some here, it definitely goes through the 300 and the 4 or 3,000 and the 4,000 as indicated, but even has enough to continue on and overpower this battery, and it's essentially recharging that battery also. So, like I said, not going to be too shocked if that's a negative. Let's see what happens. I'm kind of curious. All right, so we have 3 loops, since we're going to get 3 equations from our 3 loops. But we also have some nodes. And since we have 4 equations, we need at least 1 node. And I think this node C is a good one to write out first, because what comes in is current number 1. And definitely what comes out is current 2 and current 3. And my guess is also current 4 is coming out. That one's the one that's a little bit uncertain. Like, okay, is it coming around this way or not? But so be it if I get a negative number. All right, so I'll call that equation number 1. Now, the other 3 independent equations are the 3 small loops. Keeping in mind that if you do the small loops, you don't have to do like the big overall loop, or one that would include, if I call this left, middle, and right, I wouldn't want to do left and middle together as one big loop if I've already done the left and the middle small ones, because 2 together is mathematically nothing more than the sum of the 2. Okay. So again, I can only get 3. I mean, if you look at all the loops, there's quite a few loops you can have. You can have the left, the middle, and the right. You could have the left and middle. You could have the right and middle. You could even have the left and the right, kind of a figure 8 here. You could even then have all 3 of them together, a big overall loop. So 1, 2, 3, 4, 5, 6, 7. So there's 7 different loops I can get here, but remember, only 3 of them would be independent. And so that's where you got to be careful. And so the easiest thing for me to say, and the best way to say it, is always do the small loops. So I'll do the small loops, and maybe I'll start here at point A and go from A to B to C back to A for my left loop. So starting at A, I'd go from the smaller end of the battery to the bigger end. So that's plus 250. Then I would go against current number 4. So against it. So that's why the plus comes out there. And so this would be 1,000. So did I put a plus? Yeah. So plus 1,000 I4 and give me the C. Then I would go with the current. So that'd be a minus. And it would be 4,000 ohms I3. And I get back where I started. So all that adds up to be 0. And I'd call that equation number 2. Equation number 3, I'll do the middle loop. Maybe I'll start at A and go A, C, E back to A. All right, so from A to C, I'd be going against the current. So it's plus 4,000 I3. From C to E, I'd be going with the current. So it's minus. And that would be 3,000 I2. And then from E over to A, there is really nothing. There's no voltage change. It's just a wire. So there's nothing more to add. And that completes the loop. So that would be equation 3. Now, I'll be careful here because they actually want to know the current along this piece. And the way I have set it up so far, I don't have that. But here's where I'm getting at, is that it's how these things come together. And I can look at my numbers 3 and 4 coming down and meeting up to see what's happening between A and E. Now, I'll explain more of that in just a moment here. But let me find all these currents and these branches that we can solve for. Which one am I missing here? I haven't done, the right-hand. All right, so let me start at C and go C, D, E back to C. So C across here would be going against the current. So that's plus 2,000 I1. Then I'd go from big to little. So that would be a decrease of voltage of 500. I'm going to get to E. Then I'd go against the current. So that's a plus 3,000 I2. And that equals 0. And so that's my equation 4. So there's my 4 independent equations. This is where I'm going to get out my calculator and do another matrices. Set up my matrix equation like you guys seen me do a couple of times. So maybe I'll do it a little faster now. And so looking at this equation, I would have a 1, a -1, a -1, a -1, all equals 0. So that's equation 1 when you multiply this out. I1 minus I2 minus I3 minus I4 equals 0. That's what you get when you shift everything over to the left-hand side. Equation number 2, it looks like there is no 1 or 2 in here, but there is a -4,000 and a -3,000 for 3 and 1,000. Sorry. -4,000 for the 3 and a plus 1,000 plus 1,000 for the 4. I do that. Yeah. And then this, if I imagine moving it to the other side, would be negative 250. So there's equation 2. Equation 3 has no 1 or a 4 in it. It has a negative 3,000 for the 2 and a plus 4,000 for the 3 and nothing else. So that'd be equal to 0. There's a negative 3 plus 4 equals 0. And then this last one has a 2,000, current 1, and a 3,000, current 2, and no 3 and no 4. Would that be right? There should be for the 4 and the 1. Okay, yeah. Okay, so let me just double check that. So 3, 2,000, 3,000, and then when I bring that, that's a plus 500. All right, so there's my matrix equation. And so I'm going to reduce that to what we call the identity matrix. And so I'll just simplify it with that. And then point out that these 4 answers would be the current 1, the current 2, current 3, and the current 4. And then once we get those currents, we can actually answer the question at hand. So let me grab my matrix again, or my calculator, so I can do my matrix. And let me go to my matrix window. Let me go to edits. Let me make a 4 by 5 matrix. This is going to be a 1, enter, negative 1, negative 1, negative 1, 0. 0 and 0, then a negative 4,000, a plus 1,000, and then a negative 250. A 0, a negative 3,000, a plus 4,000, a 0, and another 0, and then a 2,000, a 3,000, a 0, and a 500. All right, now just to make sure, because I don't think we're on a time pressure, let me just make sure I entered everything. It's not like we're taking a test or a certain amount of time. Easy to mess up. 4,000, negative 4,000 plus 4,000, 0. Scroll over 1. 3,000, negative 3,000, 0 and 1. And then finally 1, 0, 0, and 2,000. So really happy with matrix A. So now let me do a little bit of math on my matrix. So I'll go to math, scroll down to the RREF, and then select matrix A. So I'll do RREF on matrix A, and it'll do the math and give me a number. And looks like that's a 0.13, 0.08, 0.06. Negative 0.01. Okay, so the negative is the interesting one to me. This tells me back here when I said that I thought it might be strong enough. I was kind of guessing it'd be strong enough to push this way, but apparently not. So the current's actually going this way. And so this current actually comes up, wraps around, and these two come in and then flare out. Okay, now what comes up here doesn't have to flare out here. These like two rivers come together and then divide again. The division of them after the flow doesn't have to equal the same as the division before them. However, when they come back up to here, they must divide again to go this way and then back that way. Here's basically what I'm trying to say is look at this right here. This is coming really up this way at 0.01, okay? And so what that means is if you look at current number 3, the 0.06 is coming this way, 0.06. And so when it gets to point A, if 0.01 goes up this way, that means veering across from A over to E must be the 0.05. And that's what they're looking for in this problem, that 0.05. And we can confirm it by checking out that as this 0.05 flows across, it's going to join up with the 2 and go up to make number 1. So if we were to take number 2 and increase it by 0.05, so number 2, which is 0.08, and we increase it by 0.05, we should get current number 1, which we do. So there's the answer to our question across this bottom. But we, like I said, we needed to figure out what this one was over here, or this one. It didn't really matter. Either one would give it to us, one, and they should confirm. One should give it to us, and one should confirm it. But it looks like then the answer that they want for number 22 would be the 0.05 from A to E. And I think I'll jump on over to the answers here too. 22, scroll down. Let's see how they do it. Oh, looks like they do some equivalent circuits. Okay. So like I got started equivalent, they stayed on it. But eventually they get to, and they write 500 milliamps, which is 0.05 amps, like I got. And they say from A to E. Okay, good. So it matches. Love it. Hope that one helped too.
Is there any questions that use the equations with the time constants in them?
Oh, yeah, and those are near the end of the chapter. So I suspect they would be further down. Well, 61 looks intriguing. Do you want to try that one?
Yeah, I'm done.
Okay. All right. So let's see. Number 61. Oh, I think we'll probably go over this time too, because 61 looks a little long. But that's fine. So let's try chapter 28, number 61. And here's what it has. It says figure 2861. Suppose that the switch has been closed for a time interval sufficiently long enough for the capacitor to become fully charged. Ooh. Now, it's actually a pretty hard problem. I can see why it's the last one, and maybe it shouldn't have been the first one I picked for demonstrating the capacitor. We should work up to this one. But they used an important phrase, and that is, they said the switch was closed for a long period of time. All right. If you ever hear that phrase, know that what they mean here is that they are going to have a capacitor that has been fully charged. But here's what makes this a hard problem, and the one that I probably regret grabbing this one first is because there is a tendency for students, and I should say beginning students, to think that when you say it's fully charged, they think it charges up to that 9 volts. And that isn't always true. And this is an example of that. what it does is in this branch right here, if this is fully charged, so we've got some pluses up here and some minuses down here, there would be no current in this side. So if I call the current coming out of the battery current number 1, and maybe I should do that in red. So current coming out of the battery is current number 1. And then when the switch has been closed, it goes through this 12,000 ohm resistor. It gets to this node. And in general, I would say it splits and goes into this capacitor or down this center branch. But you see, that would only occur at the beginning part when you close the switch after a long period of time. They're basically telling you that this capacitor has built up enough voltage, and maybe not equal to 9, but enough voltage that no more current can go down this path. Everything is essentially stopped along this path. That's essentially saying that the voltage on this and the voltage on this resistor are the same. See, these are in parallel if you kind of combine these two together. So here's what I would say. When they tell me that it's been closed for a long period of time, I would conclude that the current in number 2 is 0, which then would make current number 1 and current number 3 the same. And we have kind of a boring circuit in the sense that we're just going right through without any nodes splitting off. And so a loop would say 9 volts minus 12,000 I1, which is the same as I3, minus 15,000 I3. And again, I'll put I3, but that's the same as I1 for this moment in time when they say it's been closed for a long time equals 0. So this becomes 9 equals, and I'll just put the 12,000 and the 15,000 together. That's 27,000. And I'll just call it current 1. It doesn't really matter whether I call it 1 or 3 at this point. And then I get 9 divided by 27, which is what, 1/3. And then this would be a milliamp. So I get 1/3 of a milliamp is kind of how they're kind of expecting me to take that phrase. I haven't even really got to the question yet, but they're just saying, suppose the switch has been closed for a time interval sufficiently long that the capacitor has become fully charged. Okay. And that's what they're saying. That might be the first question. I think it is. And so A says what? A says, find the steady state current in each resistor. All right. So with the switch closed for a long period of time, we've just said that the currents, number 1, is the same as current number 3. So in other words, the 12,000 and the 15,000 will have the same because it can no longer split off. And that is 1/3 of a milliamp. I suppose for completeness, I should also probably say there would be 0 currents in the 3,000 because it does say find the steady state current in each resistor. And sometimes we overlook writing down the obvious one. All right, so that would be A. And that's what they are kind of helping you with. And that's what I guess I even did before I got to the question, just kind of looking at what do they mean by having the switch closed for a long time. Then it says, and B, the charge Q on the capacitor. All right, so now how much charge would there be? Well, remember, capacitance is charge divided by volts. So that means the charge is the capacitance times the voltage. Now, here's where understanding of our circuits is going to be really helpful, because I would say that if you look at this branch, which has the capacitor and the resistor, those two together would have the same voltage as this one resistor. Now, don't get me wrong, I'm not going to call this the equivalent of something by putting them together, but I do want to point out this, that the two voltages together really just are the voltage on the capacitor. Because remember, there's no current here. So the change in voltage on a resistor is IR. And at this moment, after we've closed the switch for a long period of time, and after there is no more current going through this capacitor, there is no voltage change on here. So when I say the voltage of these two together, I really am saying the voltage on this capacitor is now the same as the voltage here. And that's pretty easy to do. Let me get that voltage. That voltage would be IR. And the I, we already said, was 1/3 of a milliamp. So if I multiply it by 15,000 ohms, a milli and 1,000 would cancel. And so I'd have 15 divided by 3, and that's 5 volts. So again, at this particular point, we haven't even opened the capacitor. I mean, the switch up. We still just left it closed, but we left it for a long period of time. We begin to see that there would be a 5 volts here, which, by the way, would mean there would be 4 volts here, because we know the whole thing has to add up to 9, because that's the 9 there. So as the current is flowing through here, we lose 4 volts as it goes through this first resistor. We learn 5 more here for a total drop of 9, and that's how it adds up to be 9 volts. But also at the same time, whatever the voltage is on this one, which we've just discovered is 5, must be the same as the capacitor. That was important to answer this step here in B, because I know the capacitance is 10 microfarads. It's the voltage that I was unsure of. And like I said, that's what I said might make this a harder problem than I anticipated when you said you look for one. I just saw this one, but it's not the, the simpler one where it fully charges up to 9 volts. And we see that now because the 9 volts has to lose something. You have to lose some of it going through this resistor before you can even get to this capacitor. So this capacitor certainly would have to be something less than 9 volts. And so we figured out what that something less than 9 volts is. It's 5 volts. All right, so we would have 10 times 5, which is 50 microcoulombs. So there's the answer to B.
Wait, I'm sorry. Why is the voltage the same for R2 and the capacitor?
So if I were to draw something that looked like this, would you agree that these two on the right-hand side are in parallel?
Yeah.
And they have the same voltage?
Okay. Yeah.
All right, so in my mind, I'm going to change this resistor to a capacitor and a resistor.
Oh, so it works from resistors and to capacitors as well.
Yeah, so this branch here, if I connected them, would have the same voltage as that there.
Okay, gotcha.
And then, since there is no current, there's no voltage here. And so that's how I would say the voltage on the capacitor is the same as the voltage on that resistor.
Okay. And if it was still charging up, then that would not be equal.
Right. It's definitely a harder problem while it's charging up.
Okay.
Mm-hmm. Yeah. And we will see those, or they are all on either this chapter or next chapter. I think they're in this chapter too. Yeah. But in this case, well, I'm taking advantage of the what they call the steady state current after a long period of time. So made it a little easier. C, and maybe this is it. The switch is now open at time equals to 0. Write an equation for the current in resistor number 2 as a function of time. All right, well, let's come back to this circuit here. Because if you open this up, you are essentially removing this branch. So you're removing this battery, and you're also essentially removing this resistor, the 12,000. I guess he doesn't call that a 1 or a 3. He just calls this one a 2, but I'll call that number 1 and that number 2 and that number 3. So this first one, the 12,000, is essentially being eliminated. And so if I kind of redraw this, I now have something that looks like this. I have a capacitor that can now discharge through the 15,000 and around, and then also through the 3,000, but it can't do, and so I won't even draw it on here, this other branch over here. So drawing the circuit now without the battery or the 12,000, I now have a capacitor that is charged up to some value, which we just concluded is 5, not the full 9, but the 5, and it will now start to discharge through here. Now, that current goes in series through the 15,000 and then through the 3,000. So if you wanted to simplify this to an equivalent circuit, you could say I'm starting with a 5-volt charged capacitor, and I'm discharging it through an equivalent resistance of 18,000. And I'm pretty sure they don't want you to work out the math again. They want you to, go to the derivation either in the book or what I did in class and say, well, then here's what we came up with. During discharge, the currents as a function of time was equal to the initial voltage over the resistance times e to the minus t RC. So that's RC is what we call the time constant. And I think that's what you're asking about, doing a problem with the time constants. So here I would take the 5 volts and divide it by the 18,000 and e to the minus t over, and let me just come off to the side and get my time constant. So resistance times capacitance. So resistance is 18,000. And the capacitance was what? 10 microfarads. Let's see, maybe I'll just go. The numbers would give me 180,000 and then times 10 to the minus 6. And every ohm times a farad would be a second. 1, 2, 3, 4, 5, 6. So this is 0.18 seconds. So there's my time constant, 0.18 seconds. And then maybe writing this as 5 divided by 18 would be 0.278, and I didn't do 18,000, so I could write it as milliamps. So that's the initial current, and then it would decay as minus, and why don't I just, instead of writing a decimal in a fraction, go 0.18 and take the reciprocal of that and write that as minus 5.56 T to answer their question for part C, which, what was part C? Write the equation for the current and resistor number 2 as a function of time. So there's our discharging equation. And in fact, the discharging and charging equation for the current anyway, not for the charge, but for the current are the same. And then finally, D, find the interval required for the charge on the capacitor to fall to 1/5 of its initial value. All right, now, again, like for C, I don't think they want you to derive this differential equation. And likewise, I think the discharging of the capacitor, they want you to look at what they got. In fact, that's what they did. And in fact, I did too in class. I worked out the equation for the discharge and then took its derivative to get its current. So that's where this came from. But you have some initial charge, and then it follows the same exponential decay. And so whether the current is decaying away or the charge is decaying away, it's that same factor. And fortunately, we already did these numbers. The initial charge was part B, which was 50 microcoulombs. And the exponential decay with the time constant, and then even taking that in from the reciprocal and putting it in the numerator, gave us that e to the minus 5.56 t. So there would be the mathematical equation of the decay. Now it says find the time interval required for the capacitor to fall to 1/5 of its initial value. So 1/5 would be 10 microfarads. And so this is the mathematical equation I would need to solve. And so bringing this over to here would make 1/5. I'd have e to the minus 5.56 t. And now I need to do a natural log of both sides. Because if I do a natural log to the right-hand side, that gets rid of my exponential. So I need a natural log of 1/5. And that is a negative 1.609. And so now if I divide that by a negative, what was that, 5.56, I get a time of 0.289 seconds. I thought it was going to be a little longer. Let's see, maybe. Okay, I like that a little better. I'll think it through. But okay, and then I'll check the answer here too, just to make sure. But I can, again, that first part, knowing that it only charges up to 5 volts, I think is really the hard part. Let's see, 1/3. Okay, so A looks right. B looks good. Okay, let's scroll down. C, what did I get from C? Oh yeah, good. They write it as 278 microamps. Okay. And then they write it with the 0.08 in the denominator. Good, but it matches. And then they write this, oh good, as 290 milliseconds. Same thing. All right, good. We did that one. All right. No, that wasn't, I guess, too bad. I thought it was going to be a little bit longer after I saw but there is that, I think, a very challenging point that the capacitor, when it gets fully charged, doesn't go all the way up to 9 volts like it would have if you did kind of the traditional one where we just put a switch and then a resistor and then a capacitor. If you had a battery of 9 volts and you close this switch, well, this keeps building up until it stops the current, which is 9 volts. Got to get all the way up to 9 volts. But when you have it splitting off, like we had in ours, it's 9 volts. Then when it comes up here, it loses some. And in our case, we lost 4. So there was only 5 volts left by the time it got here. And that's why this branch over here only needed to charge up to 5 volts to stop the current from going down that 5 volts, because the first resistor already absorbed, if you will, part of the energy. Good. All right. Hey, well, good. It's a couple minutes past our break time. I think it's 2:10 here. So why don't I call it break time and come back and see you guys at 3 after I get something to drink for my throat. How about that?
Oh, thank you.
All right. See you in a little bit.